Hello, everybody. So we are going to discuss distributions of finite orders. So let's recall the definition of a distribution. It says that for any k, there exists Cm such that Cm such that for any phi test function with support included in k such that T of phi is bounded by a constant, the C times k less than or equal to m, phi case derivative, uniform norm. Okay, so the crucial point is that this constant C and this constant m, which is a non-negative integer, both depend on k. Okay, so the idea of finite order distribution is that if we can choose m independent of the compact set k, included in I, then we say we have a distribution of finite order. So the basic idea is that whenever the distribution involves only m's derivative, m's or lower order derivative, for the test function phi, we say it's of order at most m. Okay, so there are plenty of such examples. For instance, direct mass satisfy this example, satisfy such a condition. So we can choose m equals to 0 actually. So more, um, let's give still give a proper definition of the order of distribution. Right. So it's given in the definition 6.1. So we're given a distribution T, and then we say T is of finite order. As I said, if there exists an M, so we first define such an M, and then for any compact set K subset of I, there exists a C. Right. So we change the order of M of here, the existence of M, and for any K. So the order will be defined as the smallest m such that what I said, so this kind of inequality is true. Okay, so there are the very first example that I'm going to talk about is the direct mass. So example 6.2. So let's consider direct mass example. We have for any k, right? So there exists we're going to see what a C is. And any phi test function with support including k such that the direct mass 0 phi, by the definition it is equal to phi of 0, and this is clearly bounded by the supremum. Okay, let's just write phi uniform norm of phi. So m is chosen to be 0, independent of the compact set k, and this constant c is just a 1. So we do have, hence, the order of direct mass is 0. Okay, another example is given by the distributions associated with L1 log function. So this is our second example in here. It is of order 0 as the same as direct mass at 0. So again, it is a simple verification. Let's do the for any k there exists a constant, and we are going to see what the constant is. For any phi support including in k, we have that the TF applied to phi, f is a L1 log function. This is bounded by integral of f times phi. so that it is bounded by, um, we can pull out the uniform norm of the function phi and realize that the support of function phi is in K, so really the integral is the same if we integrate instead of the whole real line, we integrate on the compact set K. So that's what we have, right? And this guy will be a constant. This we'll call CK. So again, the order of the distribution, the order of the distribution associated with the L1 log function is of zero order. Okay, so TF zero order. Okay, let's move on to something that which is not of zero order. So we consider this time. So again, let's consider Dirac mass with a derivative. Okay, so we're going to show that this guy has order 1. So we're going to show for any k, this is the c, etc. We consider 0 delta naught prime applied to a generic function phi in here. Okay, so test function. Okay, so support is inside. Okay, so this guy is equal to phi prime of 0 in absolute value. So clearly it is bounded by phi naught, the uniform norm of that. So this actually shows that because, okay, so we can choose k less than or equal to 1 phi k. So this means yielding the following fact, which is to say that phi, this guy is of order at most 1. Okay, so we don't need to go further than that. Just 1 is enough. But we want to show equality equal to 0, equal to 1, so we want to exclude the case order 0, right? So we're going to show that this guy is not of the order 0. So we show now that delta naught prime is not of order 0. To this end, we find a compact set. We find a compact subset of I, okay, and the sequence phi j. So this sequence will be test functions. Also, their support is included in this compact set K, such that so delta, okay, such that the inequality is not satisfied. Okay, so we're going to show that actually delta naught prime applied to phi j, the sequence, absolute value divided by the supremum. So this time it's actually going to be the phi j is uniform norm. Okay, we're going to show that it's not of 0 order, so divided by 0 order derivative, uniform norm of the 0 order derivative of phi j, which is this quantity, and we're going to show that this guy goes to infinity, so that if this is true, then we couldn't find a constant, a universal constant, which depend only on k, such that this kind of inequality is true with k is equal to 0, right? So then we conclude that delta naught is not of order 0. So now it remains to find such a sequence so that we have this. The idea is to find a sequence phi j. So this sequence of functions phi j will be linear at the point 0. Okay, so on the point 0, it is like a linear function, and its uniform norm is bounded from above by, say, 1 over j. if we can find such a thing, then the ratio will be of the order j, which goes to infinity if j goes to infinity. Okay, so this is the idea, to find a locally linear function on the point x, and the uniform norm is very small. So let's do this. So the function we are going to take is set phi j x to be a linear function x times chi j of x, and this chi function is where chi j of x is going to be taken as chi of jx with so this chi should satisfy a certain property, chi a cutoff function, so meaning that chi is 1 if x is far apart from if it is close to the center to 0. It is constantly 0 if it is far away, say x is larger than 2 in absolute value, and in between it is just a value in between 0 and 1. And such function we call it the cutoff function. Then if this is the case, then we can show phi j is linear with slope 1 at the point 0, and also phi j, the uniform of that, is bounded by 1 over j. Okay, so here I draw a picture to have an idea what this function looks like. So here is the coordinate, x coordinate, y coordinate, and so our function is exactly linear because this function chi function actually is constantly 1, so does not change the value of this linear function around 0, and the support of this function is actually so we have a scaling factor j, so that the support of the function chi j is on the interval negative 2 over j. Okay, so and it is linear around point 0. Okay, something like this. So this is like negative 2 over j. This is 2 over j, and overall value of this is bounded by 1 over j. Because of our choice, right? So the maximum is obtained on the point is obtained on the point x is equal to 1 over j. Okay, so when x is equal to 1 over j, we are having this property equals to 1. And this quantity attains maximum 1 over j. Okay, and it's a symmetric function. As we can look at, we have negative 1 over j. So the uniform norm is bounded by 1 over j as claimed. So once this is found, we have that we can conclude. Thus, we have that phi prime of phi prime j of 0, so which is equal to 1 because of the linearity around 0, and phi j's uniform norm is less than or equal to 1 over j. So over the ratio is larger than or equal to j, which goes to infinity as j goes to infinity. Okay, so this finished the our claim. Okay, so we have seen that the delta naught prime is of order 1. So now I ask you to find an example find an example of a distribution of infinite order. So we already seen kind of how it works, right? So the order of the distribution relates to the number of derivatives that we need for the test function, and in order to construct the distribution of infinite order, we need infinite many derivatives. So this is the basic idea. Okay, so we define T to be the sum of the direct masses this time on K's derivative, and for all the K from 0 to infinity. Okay, so now we have a infinite many derivatives, but on different points. So this, which we can check that is a distribution. Okay, so whenever we have a compact set, we have only finite many points, finitely many of these integer points inside a compact set, so that we only need finitely many derivatives, and this shows that we have a distribution because that inequality we can establish. Okay, so such a distribution is not of finite order, precisely because of the same kind of reasoning that we did in here for the previous example. So I'm not going to repeat everything again, just to mention the idea. Okay, so the idea is to find a K. So this K this time will be of the order. Okay, let me restart. So we want to say that we show that for any m, which is an integer larger than or equal to 1, the t is not of order less than or equal to m minus 1. Okay, so if we can do this for all the m, then we are finished. We have a distribution of infinite order. Okay, in order to show this claim, so what we need to do is to find the k. So this time this k will be the interval m minus a half and plus a half. Okay, so the choice of this k is made carefully because this k include the point contains the point m, and on the m we need m's derivative, right? So if we need m's derivative for the test function, then there's no chance that we can have a distribution of order less than or equal to m minus 1. So this is the basic idea, but we need to construct a sequence. So let me continue. So for any k, for such a k, we're going to find a sequence in such a way that. So let me just give the proper definition of this this test sequence of test function: x minus m to the m times chi, which is the cutoff function we used before, j times j is a scaling factor, x minus m, m is the center that we want. Okay, so now we are done with the construction of a such function, such a sequence. Then we are going to check that. Then we have to check. Okay, so then we have the following: t phi j, which is by definition m's derivative on the point 0, on the point m, and this guy, according to our definition, if we take m's derivative, we use Leibniz rule, and whenever it is the sum of combinatory coefficient times p's derivative of the first guy, then m minus p's derivative of the second guy, right? And so this is if we So for most of the term, eventually we get 0 because we have a direct mass. We're going to take the value of such a function on the point M. If we have remains some polynomial, then eventually we have a 0. So the only non-zero term is actually the term where we take m's derivative for the polynomial and the 0 derivative for the last function. So in that case, we're going to have m factorial times chi of 0. So this is what we have. M factorial chi of 0. So this is the one thing we can check. On the other hand, we can check that for any k 0 and minus 1, if I have such a sequence, then phi j, if we take k's derivative, and we can show that this is actually bounded by a constant which depends on m times 1 over j. Okay, so again, it is we have a uniform bound for all the partial derivatives from 0 all the way to n minus 1. Okay, so combining these two results, we have that t phi j divided by supremum for all the k less than or equal to m, phi m minus 1, phi j k infinity is bounded from below by a constant which depends on m times j. This goes to infinity as j goes to infinity. Okay, so we finished the this example. All right. Now we have a bunch of example of finite orders in mind. We want to study some other properties. Okay, so very first property that we are interested in is the effect of taking a derivative for the orders. Right? So if we take derivative, how does it change the order? Also, if we make other operations such as multiplication by a smooth function, or the restriction of the distribution to a open subset, so how does it change the order? Okay, so let's look at how we can do this. So proof of proposition 6.3. So the first thing is fairly simple. So we have that t be of order m, okay, less than or equal to m. Then for any k, there exists a c for any phi test function with support inside k. We can compute t of phi, and it will be bounded by c times the supremum. Okay, the largest order of derivative that we need is m, and hence, so t prime of phi for the same set of test functions will be equal to, first of all, phi prime. And then we apply this inequality for this phi prime, which is also a test function with compact support, which is inside, the support is inside k. So that we have the c supremum k less than or equal to m plus 1 by k's derivative uniform null. Okay, so the only difference is that now we have m plus 1. And this shows that t prime is of order at most m plus 1. All right, so taking a derivative does change the order of distribution by at most 1. And so the other two claims can be shown in the same way. So we are not going to do that. The other claims can be shown in the same way, which says the following: if we multiply a distribution by a smooth function, then this distribution, then the new distribution will have the order does not change. Actually, will not increase at least. And if we take a restriction of a distribution to a smaller subset, then we also do not increase the order, which are reasonable claims, because order only involves the derivatives that we need for the test function. Okay. So now another quite nice property about distributions of finite order is that they can be extended to a much larger, a larger family of test functions. So this is the claim of proposition 6.4. So we are given, let's look at it. So we're given a test function of order less than or equal to m. Okay, and we have so we claim that we can extend T to a linear form, continuous linear form on a larger set. So this is Cm not denotes the space of Cm functions with compact support inside I, such that, okay, so this just says that we can extend T to a continuity is this property, to a continuous linear form on a larger set of test functions, which are Cn functions with compact support. So let's prove this this proposition. So this proposition probably is quite familiar to you who have learned functional analysis. When you have operator linear form defined on a dense subset of a Banach space, then you can extend it by continuity, right? So so what we do is precisely that. So proof of the proposition 6.4. So there are several steps. So first thing is that we are going to notice that any function phi Cm is compact support. We can find a sequence of test functions such that any k 0 m, we have uniform convergence. The case derivative of the sequence converge to the case derivative of the limit uniformly, like that. So by continuity, I mean for m's order distribution, we have that inequality that we use all the time. So in other words, so this is the property I meant. That's now equal to constant which depend on the k and supremum of order k less than or equal to m. Okay, by the continuity, we have that so t of phi n minus t of phi p, which is t phi n minus phi p, c phi n phi p, k less than or equal to m, k. All right, so this will be arbitrarily small if p and n are both sufficiently large. So this shows that, hence this is the limit exists. The limit p of phi n exists, and we're going to call it L of phi. It's well defined because we have Cauchy sequence. Okay, So now that we have a proper definition for any function which is not necessarily C infinity, okay, so any function Cm with compact support, we can find a sequence of test function approximating that thing. And since we have a Cauchy sequence, we can define it as the limit. Okay, this is a Cauchy sequence, so we define it as the limit. And so again, this is also alpha phi does not depend on the approximating sequence. It's not dependent on the approximating sequence, again, by the continuity. Okay, so that this is a well-defined object. And also, the linearity of L follows from the linearity of T and the limiting procedure, also, and the continuity, actually. I don't know what's going on. All right. Here we are. So the linearity and continuity and continuity and the continuity follows from that of T. So we're done. Okay. So now we are going to move to a specific class of distributions. Actually, these are non-negative distributions. So what do we call non-negative distributions are those distributions, T, such that T of phi is non-negative whenever phi takes a non-negative value. Okay, non-negative test function. So, so the claim is that non-negative distributions are all of zero order. So this is a quite important observation. Let's see how we can prove this. So proof of proposition 6.4, no 6.5. Okay. 6.6. So for any k, we're going to consider again, so we're going to make use of the cutoff function. The cutoff function. So this time, which equals to constantly equal to 1 on k, and it is going to be 0 on for all the point x, which is a little bit far away from for those x which is larger than which is of distance epsilon from k, and in between we just have 0, 1 in between 0, 1 values. Okay, so it's again the calc self function, which does not change the value of any test function inside the compact set K. So once we have such a thing, then we realize that for any test function, di with supporting K, okay, so we have, this is what I just said, so phi in absolute value is actually equal to phi absolute value times the cutoff function chi, because chi is equal to 1 on the support of the function. So we do have less than or equal to phi, the uniform normal phi, times the cutoff function chi. Chi is non-negative, and we clearly have this inequality. The absolute value of phi is bounded by uniform normal phi. Okay, so from this we have established T of phi will be smaller than or equal to T of phi uniform norm times chi, and this is because T is non-negative. T is non-negative, so that by linearity we have T times this guy minus this guy. We know that this is positive, so T times the difference will be positive, which is equivalent to this expression. On the other hand, we can also show that with a negative sign of that is also bounded from above by the same quantity. And altogether, we show that the T phi in absolute value is bounded by, so we can pull out the L infinity norm of phi times, so this time times T applied to the cutoff function chi, which is the constant. Okay, and this shows the fact that no negative distributions of zero order. So we're done with the proof. All right. So we can actually characterize all the non-negative distributions. So by a simple observation. So what we have so far is that any distribution of finite order can be extended to a larger set of test functions. If the order is 0, then necessarily, according to proposition 6.4, we can extend it to a continuous linear form on the set of continuous functions with compact support in I. And according to Riesz representation theorem, any continuous linear form can be on the space of continuous functions with compact support can be identified with a Borel positive measure. So combining these two results, we have automatically the following theorem, 6.7, which says that non-negative distributions is identified with a Borel positive measure, which is defined to be, like this. So T mu, this is our notation, like this. T mu of phi is also defined to be phi times d mu. Okay, so by combining proposition 6.4 and Riesz representation theorem, we have the characterization for non-negative distributions. So they are nothing but a Borel positive measure. Okay, so it turns out that the converse of proposition 6.6 in here, non-negative distributions of zero orders. So this proposition is almost sharp. So in the sense that we can characterize all the zero order distributions as the difference of two negative distributions. So this is very good. Here we're going to show let's show this the proof of theorem 6.8. This theorem is quite interesting. So all the distribution of zero order can be written as the difference of two positive so non-negative distributions. So in order to show this, we are going to. So first of all, observation is that we only need to show the necessity, because if a distribution distribution T can be written as just the difference of two non-negative distributions, then necessarily this guy is of zero order, because non-negative distributions of zero order, difference of two non-negative distributions will still of zero order, right? We just we have the same kind of inequality for each of the guys. Let's take a sum, then we have twice the constant than the supremum norm of phi. So we do have zero order distribution. So all we need to do is actually the necessity. So we only show the necessity. So in other words, we assume that we have a distribution of zero order, and we're going to show that it can be, we are going to construct T plus and T minus such that T can be written as the difference of the two. Okay. So the theorem can be actually split into several steps. The first step is a reduction step. So imagine that we can find a distribution a continuous linear form that we call T absolute value on the space of continuous function with compact support. Okay, so we can, if we can find such a thing, then so it has to satisfy such that so this guy plus T is non-negative, and this guy minus T is non-negative, if we can find such a thing. Then we can define as follows. T plus will be defined to be 1/2 of the sum of these two guys, and T minus will be 1/2 of the difference of these two guys. And according to the requirement we set in here, these two guys will be positive, will be non-negative. Okay, hence T can be written as T plus minus T, T plus minus T minus, as desired. Okay, so obviously the difficulty is to find such a continuous linear map which has all the needed properties, and this we are going to propose one option. We propose the construction as follows. For any phi, phi which is continuous with compact support, also we need it to be positive. This guy is defined to be the supremum of all the T applied to phi, such that phi in absolute value is bounded by psi. Okay. So we claim that this guy will do the work, and the first thing we can notice is that so T of psi is clearly larger than T of psi. Okay, T absolute value of psi is larger than T of psi because we have these requirements. This function satisfies this inequality. On the other hand, T psi is larger than or equal to T applied to negative psi. For the same reason, so this function satisfies this inequality. And for this reason, we have already yielding that T plus T, T absolute value plus T, and T absolute value minus T they are both non-negative. Okay, so it's a good start because this is what we wanted in here. So what it remains to do is to verify that this guy that we just defined is a linear and continuous form on the space of continuous function with compact support. And this is not easy to do. Okay, so the third step will be to show the linearity, but only for non-negative. Okay, for starters, we show that this is linear for non-negative functions, non-negative continuous function with compact support. Okay, so we show that for any psi1, psi2, they are both linear functions with compact supporting I, which are non-negative. We're going to show that the following star equation is true. So T absolute value applied to psi1 plus T absolute value applied to psi2 is equal to T absolute value of psi1 plus psi2. Okay, so let's do the proof of this this star equation. So we consider any, so this time phi1, phi2, which are not necessarily non-negative. It could take a negative value. And we assume that these two functions are bounded in absolute value by psi1, psi2 respectively. So then necessarily, if we take the sum, so we have by a triangle inequality that the sum is bounded in absolute value by psi1 plus psi2. Hence, T of phi1 plus T of phi2, look at this quantity, we have by linearity T of phi1 plus phi2, and because of this inequality and the definition of T absolute value, this is bounded by T absolute value of psi1 plus psi2. And then taking supremum for all phi1, phi2 satisfying this property. Satisfying this property, we have obtained T absolute value of psi1 plus T absolute value of psi2 is bounded by T absolute value of psi1 plus psi2. Okay, so this gives us one side of the identity, right? So we have an upper bound. It remains to show the opposite inequality. So now we move to the opposites. Opposite direction. So what we need to do is to consider any epsilon positive. We can find, actually you can find a phi function which is continuous with compact support, such that this phi in absolute value is bounded by psi1 plus psi2, and also the supremum is bounded. So we want to show the other inequality. Yeah. So we want to have an upper bound for this quantity, and this we can do by using the definition of supremum. We can find such a phi. Okay, this is the preliminary step. So now what we need to do is to make a decomposition of the function phi in terms of the sum of two functions, phi1, phi2, where phi1 is bounded in absolute value by psi1, and phi2 is bounded in absolute value by psi2. So if we can do that, then we can make use of the definition of t absolute value again, and bound each of the two terms by the t absolute value of psi1, psi2, respectively. So then we can then we write, we're going to do the decomposition. Phi, we're going to write it as phi plus, which is the maximum. Let me just write it out explicitly. So the maximum of phi and 0, so this and inf phi1 minus the minimum of phi, negative phi 0. Okay, wait a minute, it's going to be the maximum of the negative of x, negative phi and the 0. So now we take the infimum with actually with psi1. So psi1 are given. Okay, and then plus phi minus, and the whole thing we just defined. Okay, so this guy we just defined in here, and then we copy that in here. All right. So this is a good identity, but this will only help us if we can show. So first of all, we're going to define the first term as phi1, the second term, this guy is phi1, and the second term is phi minus phi1, which is called phi2. So this decomposition will only help us if we can show that this guy is bounded by psi1 and this guy is bounded by psi2 in absolute value, and that is true. So we can verify that. Then we see that psi1 just defined is bounded by psi1, and phi2 that we just defined is bounded by psi2. So at this stage, I think it's better to make a picture for what we just did. So here's the function. So this is the x-axis, and let's assume that we have okay. So psi1 is something like this. Okay, whatever. So just say that this is for psi1 is negative psi1, and our function, our generic function phi1, the function phi that we have in here is phi function satisfying so this properties, this phi function we have, which is very similar to, which is very close to the supremum of everything. So this guy is continuous compass pole, so I'm gonna do this. Okay, so this is our function. This is our function. Take 0 outside of this this interval, and we are going to say, so we're going to the decomposition that we did, the function, more precisely the function phi1 that we compute, we define is actually 0 whenever the function phi is 0. So in here they're all 0, and we take infimum. In here we take this is the positive part, and we take the infimum with the psi1 function. A negative part, we also take the infimum with the psi1 function. We subtract that one. So in other words, the function we have is actually follows the same value of the function phi whenever it is bounded by psi1 in absolute value. So this function doesn't change value. This part doesn't change value. It's the same. And whenever it is larger than psi1 in absolute value, we're going to replace it by psi1. So this by definition is our function phi1. Okay, so we can look at it. We can from the picture we see immediately this function is controlled by psi1, the absolute value, and as a consequence, the difference of phi and phi1 will be controlled by psi1 because phi is controlled by the sum of its two in absolute value. All right, so now we are good. We have such a decomposition, and we are almost done for this step. Hence, we have say that this psi1 plus psi2, recall that this is the supremum of all the functions which is bounded by psi1 plus psi2 in absolute value. And that one is bounded by epsilon, that is arbitrary. And we have find the decomposition for the function phi. We know that this is this. And we have find the decomposition for the function phi. And we also know that each one of the phi function, the phi I function is bounded in absolute value by psi I function, I equals to 1 and 2. And by using the definition of T absolute value, we have this bound. And from here, letting epsilon goes to 0 gives the opposite inequality. And that finishes the proof. Of star. Okay. Recall what is star. Star says that for non-negative functions, we do have linearity for this new defined T absolute value. Okay, so this is very good. But still, we need to define it. We need a distribution. We need the linearity for all the functions, and we haven't defined what it is yet. So let's do the finish the step. Again, linearity, but this time for generic functions, general continuous functions with compass support. So this time for any functions, first of all, let's define what is T absolute value for generic continuous function. So our definition is based on a decomposition, any decomposition actually. Where phi, let me emphasize the fact that we don't care about a specific form of the decomposition. For any decomposition, phi is phi plus minus phi minus phi minus with non-negative phi plus phi minus, which are both continuous with compass support. Okay. So one of the possible option is, of course, to take phi plus to be the maximum between phi and 0, and the phi minus to be the maximum between negative phi and 0. And but what is really important here is that this value does not change if we change the decomposition, right? So if we do any decomposition, eventually we have the same quantity. So this is something non-trivial. So let's check this fact first. So we check that T absolute value of phi, this value does not depend on the decomposition of phi. So in other words, we are going to assume that phi can be decomposed in two different ways. Tilde plus minus tilde minus. Okay. So if phi can be decomposed in two different ways, and we're going to show that this quantity with phi plus phi minus and phi tilde plus phi tilde minus will give the same quantity in here, and so we have a well-defined definition. Okay. So if we have this, then one thing we can say is that phi. So let's move the terms. We have phi plus phi tilde minus is equal to phi tilde plus phi minus. Okay, so both are positive. So that's the important point. Since both are positive, we can define. We know what this quantity is, and we have just checked in step 3 that it satisfies linearity, so we can separate these two terms. Phi tilde minus. On the other hand, since we know that these two guys are the same, so we have the identity in here. Phi tilde plus phi minus. Again, linearity for non-negative functions, we have this. And this shows that these two sum are equal. And if we rearrange the terms, we're going to have t absolute value of phi plus minus phi minus, t absolute value of phi minus is equal to t absolute value of phi tilde plus minus t absolute value of phi tilde minus. So in other words, we have obtained phi tilde plus minus phi tilde minus is equal to t absolute value phi plus minus t absolute value phi minus. So this is our claim, that this does not depend on the particular choice of the decomposition. So this always gives the same value. All right. So this is a starting point. So we have defined t absolute value of a generic C continuous function with compact support, not necessarily non-negative. So now we want to show the linearity. How do we do that? So let's consider now for any phi 1, phi 2, which are continuous function with compact support. And we have phi 1 plus phi 2. We consider this. We want to show that it is equal to t absolute value of phi 1 plus t absolute value of phi 2. So first we realize that we rewrite it. So we realize we can write it as phi 1 plus minus phi 1 minus plus phi 2 plus minus phi 2 minus. So any decomposition works, right? So the only requirement that we need is that these guys are positive, these guys are non-negative, right? And such that phi 1 is equal to this difference, phi 2 is equal to that difference. And we observe that this guy plus this guy is positive, this guy plus this guy is positive, so we have another decomposition. And according to our definition of t absolute value, so this is equal to, so we rearrange term. Okay, and again, by using linearity, so we can put these two things together plus these two things together, and we eventually have phi minus plus t absolute value phi 2. So this is precisely the linearity we have. Okay, so this at least this is part of the linearity. So moreover, we can show it is easy to show that we have homogeneity. So t absolute value of lambda for any lambda times psi is equal to lambda times t absolute value of psi for any lambda. So linearity is okay for generic continuous function with compact support. So we are almost done. We have shown that the existence of such a linear form, which is larger than t and the negative t, and all that remains. Let's go back. So all that remains, we have shown that it's a linear form. And we have shown that these things are also true. All that remains is to show the continuity. So this is the last step. Continuity. Suppose 5. So since t is of order no larger than okay, so t actually is of order 0. So we know that for any compact set inside included in I, there exists a constant. Any phi continues with compact support. Support is in K. We have this. Okay. So now we can write phi. So this time we're going to use a specific decomposition of phi. Phi plus this time will be the supremum of phi and the 0, and the phi negative will be the negative phi sup 0. So then we have, in order to show continuity, we're going to bound it from above this quantity, and this is equal to, according to the definition, phi plus minus t phi minus. Okay, so it's bounded from above. We look at each of the terms. So this term, according to the definition, is the supremum of t of phi, which is bounded in absolute value by this quantity. Since t of phi is bounded by this, and each of the absolute value, the uniform norm is bounded by the uniform norm of this guy, right? So we have the constant, which is the same constant as in here. So constant times is uniform norm plus c negative uniform norm. And according to our choice of this phi plus phi minus, each of them is bounded by phi the uniform norm. And this shows that this linear form is continuous. And we are done with the proof. All right, so one more thing before we finish this section of distributions of finite order. So now we know that we can represent a distribution of finite of zero order as the difference of two non-negative distributions. So we can make a another representation which says that any distribution of zero order can be written as a positive Borel measure with density f. F is an L1 log function. Okay, so this is actually the combination of our previous characterization result and proposition 4.6, 6.4. Okay, let's do the the proof of it is fairly simple. So proof of corollary. So since t is of zero order, of order zero, by the previous theorem, we have 6.7, 6.8. So we can find a bunch of, so 4 Borel positive measures such that our distribution is written as T1 minus T2 plus I times T3 minus T4. Okay, so this of zero order, we know that it can be written as the real part can be written as the difference of two non-negative distributions, and the complex part can be written as the difference of two non-negative distributions. And each of the non-negative distributions is associated with a positive Borel measure, mu1, mu2, mu3, mu4. Okay, and so this Ti is precisely T mu I for any I. So now we can define mu to be equal to the sum of the four Borel measures. Then by Radon-Nikodym theorem, we know there exists density F1, F4, each of them is bounded in between 0 and 1, and any continuous functions with compact support, we have the integral phi d mu I is the integral phi f times fi times d mu. Okay, so that t can be written as t associated with f. So this is a new measure. This is actually signed measure, f d mu, with f given by f1 minus f2 plus I times f3 minus f4. All right, so this finished the proof of the corollary. So any zero order distribution can be written as a Borel positive mass measure with a density f, which this so density could be negative, of course, and it's actually a L1 log function which takes a complex value. Okay, so this actually finishes the section about finite orders. So what we want to do next will be to consider distributions with several variables, and most of the theory has been done already in one dimension, and most of the time we don't need to do a lot of much more work to extend what we knew already to this new case. All the proof can be generalized, and most of the basically all the results that we have seen already remain true. And for instance, let me just end this section with a bunch of definitions, and you will see that they are exactly the same as before. So no surprise. First of all, we have a test function. So what do we call the test function? Is still C infinity with compact support. Okay, so with an open set. So now we consider open set instead of open interval. So the convergence is for the test functions is the same. So now we consider multi-index, the partial derivative with multi-index, and the distribution is defined to be a continuous linear form. If we have the notion of convergence, we can talk about continuity. So now we can take a partial derivative for distribution, which we pass to the test function with -1 to the power alpha, the norm of alpha, which is defined to be alpha 1 plus alpha d. So the product by a smooth function is defined the same way. We pass it to the test function. And finally, so we consider the restriction of a function of the distribution to open set defined in the same way. The support of the distribution the definition doesn't change. Convergence of distribution the same, and order of the distribution the same. Okay. So as I just said, all the results basically remain the same. And there are some new results in higher dimension, and some techniques in one dimension might be should be generalized, and there are some complication from that. So we're going to cover all the stuff, all the new stuff about distributions in several variables next lecture. Okay, this is it. See you next time.